Hello everybody. This talk entitled Beam Focusing by Scattering from an Array of Scatterers on a Drone is a joint work of Neil Egarguin and Dr. Daniel Onofrei from the Mathematics Department and Drs. David R. Jackson, Julian Leclerc, and Aaron Becker from the Electrical and Computer Engineering Department, all of the University of Houston. Here's the outline of the talk. First, we shall start with a brief description of the proposed concept. Then we'll talk a bit about the mathematical framework and optimization scheme that we employed in order to achieve the desired scattering effects. And finally, we'll show some of the results of our simulations, featuring some good achievable beams, the effect of mutual coupling among the elements, beam steering via simple rotation of the drone, and a dynamic nulling scheme. Alright, so let's begin as promised on a brief description of the concept. So in some scenarios, it might be desirable to relay a signal from a transceiver, such as this one, to a distant transceiver when there is a blockage and thus no direct line of sight between the two transceivers. The distant transceiver might be located on the ground, such as this one, or possibly on an airborne platform. Well, the concept we propose here is the use of a drone as a relay. A single antenna located on the drone will produce a fairly broad radiation pattern in the relayed signal, which may be less than optimal. So what we propose here is the use of an array of scatterers so that we can radiate a focus beam that points towards the distant transceiver. The figure on the right shows a drone carrying an array of scatterers with a predetermined horizontal layout. We keep the vertical position of each scatterer on the drone as a degree of freedom to control the phase of the signal scattered by the particular element. The array of scatterers thus acts as a phased array, with the radiated beam properties dependent on the vertical positions of the scatterer for a given horizontal layout. So the transceiver, located, say, on the ground, will transmit the signal, which will then be scattered by the array carried by the drone. The radiated pattern of the array of scatterers will then depend on the position of each element with respect to the transmitter on the ground. We let x sub s, y sub s, and z sub s be the coordinates of an arbitrary spot on the drone, which we can take to be the center of the swarm, and theta s and phi s be the polar and azimuthal angles, respectively, of this point relative to the transmitter on the ground. For practical purposes, the array has a fixed horizontal configuration, and by simply adjusting the heights of the individual scatterers within the array, we can create a beam focused in some prescribed direction, such as this one, which is focused at 0 degrees in the azimuth plane. Assuming identical scatterers and neglecting the mutual impedance, the 3D far-field scattered pattern magnitude for an array of n scatterers is given by this function f of the polar and azimuthal angles of an observation point in the far field. Here, r sub n is the distance from the ground-based transceiver to the nth scattering element. This pattern gets multiplied by the element pattern for the scatterers, which for our purposes we assume to be simple resonant vertical dipoles. If the drone is far enough away from the ground-based transceiver, this far-field approximation may be used for r sub n, given in terms of the distance from the ground-based transceiver to the chosen center of the array. Throughout the talk, we shall use prime coordinates to denote the locations of the center of the nth scatterer relative to the chosen center of the array. Our foremost goal is to achieve a beam focused in an a priori chosen direction. For a given horizontal layout of the elements, we can find the vertical position or height of each element to achieve beam focusing. One way to do so is to enforce that all elements radiate a scattered field that is in phase with a given or chosen direction. This gives us the following beam focusing condition. We start by determining a good horizontal configuration for the array. We pick a symmetric array layout to allow for beam steering by simply rotating the drone. For instance, in the case of 9 array elements, we use a double cross formation as shown in this figure. The parameters d1 and d2 representing the distance between the central element and the elements on the two crosses are chosen so that the generated pattern is focused at theta 0, phi 0 with minimal side lobe levels. In the expression at the bottom of the screen, we used f sub s to denote the pattern outside the main beam. For our first simulation, we tried to produce a beam focused on the direction 90 degrees on the polar plane and 45 degrees on the azimuthal plane with a 3 GHz operating frequency. We calculated the optimal horizontal configuration to be the one with d1 equals 4.5 centimeters and d2 equals 4.83 centimeters. The horizontal position and the resulting element distribution after the beam focusing condition is imposed are shown on the slide. Here we see that the elements can be arranged on a 10 cm by a 10 cm platform that can easily be attached to a normal drone. Here is the generated pattern on a polar plot. Here we indeed see that the beam is focused at the desired direction and the maximum side lobe is just negative 11.23 dB. Now that we have a predetermined horizontal arrangement of the array elements, we can use the elevation z sub i's as degrees of freedom to further improve the pattern shape. To this end, we solve for the minimizer of the cost functional little f defined as follows. Each of the four terms in little f represents a certain characteristic of the pattern. Each is weighted by an optimization parameter lambda sub I, which determines the bias for each term. The values of these weights are determined using a parameter sweep. The first term forces the beam to be focused at theta 0 phi 0 since we will not have the beam focusing condition anymore. The second term aims to lower down the side lobe level. The third term gives us the option to create a null at the direction theta null comma phi null, while the last term increases the directivity of the beam. The cost functional f is non-convex and has a lot of local minima. This makes the optimization sensitive to initial guesses for the minimizer z. This optimization problem is solved using MATLAB's fmincon routine coupled with its global search algorithm. Now for this simulation, we want to create a focus beam at 90 degrees, 45 degrees with high directivity and minimal side lobe levels while having a null at 45 degrees, 315 degrees. And then we shall use the optimal horizontal double cross configuration that we have obtained earlier. And here are the set of optimization weights which we obtained via a parameter sweep. After performing the optimization procedure in MATLAB, we obtained the following element distribution. The figure on the left shows the optimized elevations ranging from 96 meters to 102 meters, while the figure on the right shows the 3D view of the optimized positions. Then we look at the resulting radiation patterns. The generated pattern at the horizon, that is at the theta equals 90 degree plane, is shown in these plots. Here we see a focus beam at phi equals 45 degrees with maximum side lobe of just about negative 16.26 dB. Meanwhile, the 3D pattern is shown in the color plot. Here the color scheme was truncated to a minimum of negative 40 dB. We see that a very small value of negative 176.18 dB was generated in the given null direction. The beam has a 3D directivity of about 10.90 dB. In the previous simulation, we did not account for the effects of coupling between the scatterers. Such effects can be incorporated in a mathematical framework by computing the mutual impedance and use this to find the current amplitude for each element. However, several of our simulations suggest that the effects of mutual coupling to our optimized array are not that significant. We take the optimal horizontal locations and elevations computed using the scheme we described earlier, but now calculate the far-field pattern with the effects of coupling considered. The maximum side lobe level on the horizontal plane may rise by at most a couple of decibels, but the relative difference between the patterns are about 3%. In this slide, we see the results from the simulation we performed earlier on the left and the calculated pattern when coupling effects are accounted for on the right. At least visually, we see little difference between the 3D patterns except on some patch around the phi equals 260 degrees and theta equals 130 degrees direction. The maximum side lobe level increased by just about 0.74 decibels, while the directivity dropped a little bit from 11.34 dB to 10.94 dB. Another interesting application is to refocus the beam towards another direction. One way to do this is to recall the drone back to the ground base, rerun the optimization routine with the new focus direction, and readjust the elevation of the scatterers. A fancier mechanism can also be attached to the drone to adjust the element elevations mid-air. Both methods require a rerun of the entire optimization framework, and the latter will require a mechanical component to be attached to the drone. An easier approach is to simply rotate the drone by some angle phi sub r so that the horizontal position of the array elements are now functions of phi r while the elevations are fixed. However, this scheme is efficient only for some rotation angles near the focus angle initially used in the optimization routine. Here we see the advantage of choosing the horizontal layout of the elements to be symmetric, as a good pattern shape is preserved for a wider range of rotation angles. For the following drone rotation simulation, we focus on optimizing the 2D pattern. Moreover, to fully take advantage of the problem's symmetry, we run the optimization to achieve a focused beam at an initial angle phi 0 equals 0 degree. This makes the elevations computed using the beam focusing conditions symmetric. The optimal double cross configuration has D1 equals 6.47 centimeters and D2 equals 2.13 centimeters. The cost functional in the final optimization only has 3 terms, since we will be dropping the term for the null direction as we shall introduce an alternative approach for null creation later. Moreover, all of the terms just use the 2D pattern. Then when we compute the optimal elevations, we impose symmetry on pairs of elements. This shrinks the number of unknowns from 9 to only 5. The calculated element configurations are shown in the figures on this slide. Notice that in the plot showing the elevations in the lower left, element number 2 is a central element, and the pairing of elements with symmetric elevations are 1 and 3, 4 and 5, 6 and 7, and 8 and 9. The resulting pattern is given in the following plots. The maximum 2D side lobe is minus 18.74 dB with 2D directivity of about 8.17 dB. We then rotate the drone, hence rotating the position of the elements, and observe the key characteristics of the new pattern. The new angle phi sub f on which the beam is focused and the 2D side lobe levels, as well as the directivity, are shown in the following figures as a function of the rotation angle phi sub r. We observe that from plot A that there is always a rotation angle that can refocus the beam at any new angle phi sub f. However, the side lobe level rises to undesired values for large rotation angle as seen in plot B. There is also a similar degradation of the pattern's directivity as seen on plot C. This result suggests that we can afford rotating the drone by about plus or minus 30 degrees with no significant drop in the pattern quality. This animation shows the pattern evolution as a function of the rotation angle. This better illustrates the information suggested by the plots in the previous slides. Indeed, one can observe that the good pattern shape was maintained for rotations within the plus or minus 30 degree range. Here we have an animation that shows that the results we obtained maintain the desirable properties for certain frequencies. This is complemented by the still plots on the right showing the side lobe levels and directivity as a function of the relative frequency. These results suggest that to maintain good side lobe levels of about minus 15 dB or below, we need to be within 98% to 106% of the central frequency. Lastly, we show a simulation with a dynamic null creation, that is, imposing a null or near null pattern at different directions. We start by running the optimization routine to find the elevation so that the beam is focused at some direction, has minimal side lobe levels at the horizon, and high 3D directivity. Notice that in this optimization we do not impose a null condition yet. Then to achieve a near null pattern value at some direction theta null phi null, we load the central element with an amplifier that controls its current amplitude and phase. This amplifier gives us a degree of freedom, a complex number A that can be algebraically computed so that the pattern magnitude at the given direction is exactly 0, resulting in this value of A, or as a solution of the nonlinear equation where we equate the pattern magnitude at the given direction to minus 40 dB. For some null directions, this amplifier has no significant effect on the side lobe levels and directivity. Here are the results of our simulation. The info on the left half of the slide shows the results of our initial optimization without any null condition. The right half of the slide shows the results after loading the central element with the purpose of creating a null at 105 degrees, 260 degrees. Notice that in the original pattern, the value at this null direction is about minus 16 dB. Then aside from creating a null, we have maintained a fairly good pattern shape. We are also working on several extensions of this research which may be of interest in different application areas. Some of these topics are listed in the slide. And that's it for our presentation. Thank you for your attention, and we would love to hear some questions from you.